Good evening, class. Here's Calculus 1, Chapter 2 review, Limits and Derivatives, from section 2.1 to 2.8. Here's the second part. 2.4, the precise definition. 2.5, continuity. 2.6, limits at infinity, horizontal asymptotes. So here's the precise definition. Limit of f of x as x approaches 3 equals 5 means f of x is close to 5 when x is close to 3. So in short, if we look at number 3 along the x-axis and we come and approach 3 from the left and right, and we have the distance of delta from each side. It's that delta is a very small number. We approach the number of interest in this case is 3. Along the y coordinate, we approach 5, and again, the distance of epsilon. Okay, so we are somewhere here. That's the idea of the limit. So I'm going to read this. This statement reads, whatever epsilon larger than 0, there exists a delta larger than 0, such that if the absolute value of x minus a is less than delta, this is meaning a is 3 in here. Look at the distance from both sides. That's why with an absolute value. Then the absolute value of f of x minus L, in this case, the L is 5. It's less than epsilon. Now, we can make the values of f of x within an arbitrarily distance epsilon from 5 by restricting the values of x to be within distance of delta from 3, but of course, not x equals 3. If 3 minus delta less than x, 3 plus delta. Remember, when you have an absolute value, you can drop the absolute value if this value is positive, and it is the case. You can sandwich it between a negative and positive value. Okay, so that's what happens here. X minus a is between negative and positive delta, and then you move the a to the others. Then 5 minus epsilon less than f of x less than 5 plus epsilon. By taking the values of x not equal to 3 to lie in the interval of 3 minus delta and 3 plus delta, right here. We can make the values of f of x lie in the interval of 5 minus epsilon and 5 plus epsilon. That's the meaning of it. It's extremely close to the limit, namely number 5. Precise definition of limits. Let f be a function defined on some open interval that contains a except possibly at a itself. We say the function has a limit at a if the limit of f of x as x approaches a equals L. If for every small number, epsilon larger than 0, epsilon is a positive number, but it's extremely small. There is a number delta larger than 0, which is small. Again, delta is a positive number, extremely small, such that if x minus a in the absolute value sense is between 0 and delta, then absolute value of f of x minus a is less than epsilon. And this is the concept. Now, in other words, as far as the domain, remember, x is the domain, y is the range. The domain is concerned somewhere between a minus delta and a plus delta, that's the x value, somewhere between L, the limit minus epsilon, and limit plus epsilon, where we land. That's the concept of a precise definition, and we're going to move on. Use the graph to find delta, such that the absolute value of x minus 3 is between 0 and delta, then the absolute value of f of x minus 2 is less than 0.5. I'm going to remind you of what I mentioned the previous page. The definition of the precise definition of a limit says whatever epsilon larger than 0, there is a delta larger than 0, such that if the absolute value of x minus a is less than delta, therefore the absolute value of f of x minus n is less than epsilon. Okay, so in this case, guessing a value for delta given epsilon larger than or equal to 0, we need to find or guess sigma larger than 0 such that if the absolute value of x minus a is between 0 and delta, then f of x minus l, the absolute value is less than epsilon. That's the idea. Of course, this one, the graph actually is giving you the answer, but I want to show you the general methodology to work. Before we do that, I want to remind you, if the absolute value is less than b, where b is a positive number, then you can drop the absolute value and sandwich it between the negative and positive values. So again, although we can read it from here, I want to just make a point. If you want to go look at the proof, you start from here. And you start from here and you write what you have. F of x minus 2 less than 0.5. This is what we have. By methodology that is mentioned here regarding the absolute value, drop the absolute value, make it between negative and positive 0.5. Add 2 to 3 sides. And f of x is between 1.5 and 2.5, as you can, of course, see from the graph. It's given. But what if the graph was not given? You could figure out what it is. Now, we want to use the graph to find the value of delta. So from the graph, we are looking at this distance or that distance, 3 minus 2.6 or 3.8 minus 3. In essence, x is somewhere between these two numbers as the graph indicates, between 2.6 and 3.8. So what is this distance? 3 minus 2.6, 0.4. What is this distance? 3.8 minus 3 is 0.8. So take delta, the minimum of the two distances, either this one, which I said 3 minus 2.6 is 0.4, or this one, which is 3.8 minus 3, which is 0.8. And of course, which one is the smaller value? 0.4. And by the way, any number smaller than this minimum value will do the job. This is extremely important to understand. Now, why do we choose the smaller of the two? Let's just make sure we understand that. If we choose the larger one, okay, if you choose the 0.8, this goes beyond that, and then it puts you outside the limit because you have to subtract. If you go with 0.8, distance of 0.8, then 3 minus 0.8 gives us 2.2 somewhere here, which is outside this limit. That's why you choose the smaller of the two. And any number in between, any number smaller than that, just think about it. Pick a number smaller than that, will do the job. Because the worst case scenario is the one that is large. Again, I'm writing the definition that I mentioned here. And we want to prove the limit of 4x minus 7 as x approaches 3 equals 7. As you know, we just plug in. But quickly, as far as the precise definition and how it works, is that you start writing out this one. Okay. So in essence, if absolute value of x minus a is less than delta, absolute value of f of x minus l is less than epsilon, it means we are going to write if absolute value of x minus what is a, number 3, is less than delta, f of x, what is f of x? 4x minus 5 minus L, what is L? 7. So replace the A with 3, replace f of x with the function given, which is 4x minus 5, and replace the limit with the limit that is given in this case 7. And we always start with the second part, in this case, this one. And we are going to move this in a manner that looks similar to this or a multiple of that. So let's see what happens. 4x minus 5 minus 7 is 4x minus 12. I can factor number 4 out. So 4 times the x minus 3 in an absolute value, I can take the 4 out because the absolute value of 4 is 4. Divide by 4. And now put this one next to it. So compare to the absolute value of x minus a less than delta and choose delta. So when we compare, what do we notice? If the left side is the same, the right side must be the same. We can choose delta to be epsilon over 4. And believe it or not, that's all that matters. You want to find a relationship between delta and epsilon, both of which are extremely small numbers. Both of these are extremely small numbers. Now, the proof is to work backward, showing that this delta works. Reverse this step. So this piece and this piece. If you start with this one and you let delta be epsilon over 4, all you have to do, because this is epsilon over 4, you're going to multiply by 4. If I multiply both sides by 4, this one gets 4 times, this one gets 4 times delta equals epsilon. So we are reversing the process. In essence, we are moving this way. I can take the number 4 inside, and it becomes 4x minus 12. See? And 4x minus 12 is the same as 4x minus 5 minus 7. And that looks exactly like what we had there. You can see that. And from here, you can get here. That means if the absolute value of x minus 3 is less than delta, then the absolute value of 4x minus 5 minus 7 is less than epsilon. Then this limit, the limit of 4x minus 5 as x approaches 3 must be equal to 7. And let's look at the graph. As we look at the graph, here's along the x-axis 3. You go to the left and right by delta. Here's the limit 7. You go up and down by epsilon. And that's the concept that the limit indicates for us. Here's the summary of continuity. A function has a limit at a if the limit of f of x as x approaches a from the left equals n, the limit of f of x as x approaches a from the right is n, and the limit of f of x as x approaches a equals l when the two one-sided limits are identical. And it becomes continuous when it's equal to its functional value. Now, direct substitution property. For polynomials or rational functions, if the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. In other words, limit of f of x as x approaches a equals f of a. A function is continuous if the limit of f of x as x approaches a exists and it's equal to f of a. That means the functional value. So I hope that's pretty clear, everybody. The function is continuous from the right if the limit of f of x as x approaches a from the right is f of a, and it's considered continuous from the left if the limit of f of x as x approaches a from the left is f of a. Needless to say, it is discontinuous if it happened to be discontinuous at a. The intermediate value theorem, short IVT. If f of x is a continuous function on the closed interval of a to b, so you have a closed interval of a to b, and you have a continuous function, and let n be any number between f of a and f of b. F of a, f of b, and n is some number in between. You can draw a horizontal line, y equals n. And remember, this function is continuous. And n be any number in between where the two values are not equal, and that's the point. There must exist a number c in a and b such that f of c equals a. In other words, if you know the function is continuous and the functional values at the endpoints are different, then somewhere, if you have a number somewhere in between, the function has to cross that. More importantly, this is used to find intercepts. In other words, they look at the case that f of b is positive, f of a is negative, and this function is continuous, so it has to go through the x-axis, resulting in a root or zero of a function. That's the usage of that. Determine C such that P of x is continuous at x equals 5. And again, reminding you, CTS for short means limit of f of x as x approaches a equals f of a. Well, first, we want to take the limit of this function. The limit of the function as x approaches 5 uses this one because although it's a piecewise defined function, in the case where x is not equal to 5, less or larger makes no difference, we use the same thing. So let's find the limit first. As you can see, if you plug in, you get 0 over 0. And this is x squared minus 25, a squared minus b squared. So you can factor it into x minus 5x plus 5. Okay. We drop the common factor and we plug in and we get 10. Now, the limit is 10. The functional value is c. They must be equal. So the limit of p of x as x approaches 5 equals p of 5 equals c. If we want continuity, then the choice for c must be 10. Show that the function is continuous from negative to positive infinity. F of x is a piecewise defined function. Sine x if x is less than pi over 4, cosine if it's larger than or equal to pi over. Reminding you that these are trigonometric functions, continuous from negative to positive infinity, each one. Therefore, this is continuous in its domain of negative infinity to pi over 4. This is continuous from pi over 4 to infinity. But what happens at the end? In other words, we know the function is continuous from negative infinity to pi over 4, union pi over 4 to infinity. And we don't know what happens at pi over 4. We have to check it. So the only point that needs to be checked is the end point, namely pi over 4. So we're going to look at the limit from the left and right and a functional value. So the limit of f of x as x approaches pi over 4 from the left uses less than this one, and as you know, sine of pi over 4 is squared up to over 2. We're going to look at the right side. The limit of f of x as x approaches pi over 4 from the right be larger than we look at the bottom piece cosine. And again, you know, cosine of pi over 4 is also squared up to over 2. One more thing we need to look at, and that is functional value f of pi over 4. So you have to go with the equality, choose the second piece. And since they are all equal, The limit of f of x as x approaches pi over 4 is f of pi over 4 equals square root of 2 over 2. F is continuous at pi over 4, which makes it continuous now from negative to positive infinity. Types of discontinuities. As you can see, we have a rational function and there is a hole here. We have the same rational function, but we are defining the functional value at 2 to be 1. So obviously the two are discontinuous. So we create a hole in a case of a rational function if there is a common factor between the top and the bottom. So when we factor this, we can drop the common factor of x minus 2, we get x plus 1. Please understand the function y equals x plus 1 or g of x equals x plus 1 is the line that is continuous and it doesn't have a hole. So the difference between this function and this function is that this one is a line with no holes. This one is a line with a hole. This one also has a functional value defined at 1. In other words, this one has coordinates 2, 1. So this is called a removable discontinuity. Parts A and C, removable discontinuities. We could remove the discontinuity by redefining f of x at just the single point number 2. So although it's a discontinuity, it's not too bad. We can fix it. Why? Because there's only one point missing. And all you have to do, redefine it. The way you redefine it, if you plug the 2 in here, you get 3. So if you would redefine this as 3, fixes the problem. However, if you look at these two cases, this is called an infinite discontinuity or vertical asymptote. This is called a jump, and there's nothing we can do to fix it. So those are types of discontinuity: removable discontinuity, jump, uh, uh, vertical asymptote, or infinite jump. Those are the types that we have. So at what point or points is f of x discontinuous? Namely, discontinuity if removable. How would you redefine to remove it? First, we're going to go along the x-axis and start from left to right and see where we can see the discontinuities. Obviously, at -2, okay. At -0.5, 0, 1, 3, 5. So those are the discontinuities. But what type are they? Well, first let's look at the bad ones. Obviously, we have a jump at 0. If you look at 0, it jumps from here to here. If you look at 1, it jumps from here to here. So 0 and 1, they're both jump. What about this one? This is not good either. Infinite or vertical asymptote. So number 3 is infinite or vertical asymptote. The rest of them are all removable. That means -2, -0.5, and 5 are removable discontinuities. That means there is a way to fix them, and that's what we are going to discuss. So let's start with negative. So along the x-axis, the first one that is removable is -2. So if we approach a -2 from the left and right, from the left we are moving this way, from the right we are moving this way towards this point which has a y coordinate 2. Therefore, if the limit exists and it's equal to whatever, in this case happen to be 2, therefore we redefine as f of -2 being equal to 2. That fixes the problem. Then the next number is -0.5. Look at negative 0.5 and we approach it from the left and right. From the left, we are going this way. From the right, we are going this way, but both of them are moving us towards this point, and this point seems to have a y coordinate of 3.5, then the limit is 3.5. The limit of f of x as x approaches negative 0.5 equals 3.5. Since the limit exists, all we have to do, redefine f of negative 0.5 as 3.5, and that fixes the problem. The last number is 5. Let's approach it from the left and right. Left going left this way, going this way. Right this way, going this way. Both of them move us towards this point. And this point has a y coordinate of 5. The limit exists and it's equal to 5. And so all we have to do, say f of 5 equals 5, and that fixes the problem. So in short, there are different types of discontinuities. The removable ones, that means they have a limit. The limit does exist. So redefine the functional value to be equal to the limit for each case, and they are fixed up. The other ones, there's no way to fix them. A jump, a vertical asymptote, you can't fix it. Use the intermediate value theorem to show that there is a root for this equation between 1 and 3 sine x equals x squared minus x. So reminding you, the intermediate value theorem says if f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b, where the two values are not equal, there must exist a number in the open interval of a to b such that f of c equals to. So we are looking for the root, that means the zero of a function. So you look at what happens, and it doesn't necessarily happen at the end points, but first, the function f of x, you can bring everything to the left or to the right. It's your choice, makes no difference. It creates a function, and you set it equal to 0. That's what we are looking to find. There is a root for this equation. You can say a root for this equation, or you set this one equal to 0, means absolutely the same thing. So having said that, please understand this function is continuous from negative to positive infinity. And why is that? This piece is a polynomial function. This is a sine. Each piece is continuous from negative to positive infinity because it's a combination of a polynomial of degree 2 and a sinusoidal function. So let's look at 1. Let's plug in. F of 1 is negative. Let's see how we know that. So let's plug in. If we plug in, I hope you realize that you do get 1 minus 1. They cancel each other. You get minus sine 1. You don't even have to know what it is to know that it is negative, because sine 1 is positive. By 1, we mean 1 radian. It's about 57 degrees. So minus sine 1 is negative. Now let's plug in 3, and 3 makes it positive. Let's see how it works. If you plug in, nine minus 3 is 6. And 6 minus sine 3 is positive. Why is that? Because sine of 3, you don't even have to know the number. Sine is between negative 1 and 1. Worst case scenario, it's 1. That makes it 5, which is not, by the way. So because 1 is negative, 1 is positive, and 0 is in between, then according to IVT, intermediate value theorem, f of x is continuous on the interval of 1 to 3, closed interval of 1 to 3, and has a root somewhere in between. So that's by IVT. Limits of functions at infinity. Here's the summary. Definition: horizontal asymptote or HA of the curve y equals f of x is y equals L. The limit of f of x as x approaches negative infinity or positive infinity is L. That's the definition of a horizontal asymptote. And then y equals L becomes the horizontal asymptote. For example, we know the limit of 1 over x as x approaches infinity is 0, and the limit of 1 over x to the power of p as x approaches infinity is 0 as long as p is larger than 0 or positive. For example, let's look at an exponential growth in the form of y equals b to the power of x, where the base must be larger than 1. Example, exponential function with the base e natural log. This is an exponential growth where b is between 0 and 1. As an example, e to the power of x, the limit of e to the power of x as x approaches minus infinity is 0. And that indicates, of course, that the x-axis of y equals 0 is the horizontal asymptote. And the limit of f of x as x approaches infinity is infinity. This one, the limit of f of x as x approaches negative infinity is infinity. As an example, the limit of e to the power minus x as x approaches infinity is 0, which indicates the horizontal asymptote is y equals 0. Y equals x cubed. Everybody remembers the first and the third quadrant? Okay. The limit of f of x as x approaches negative infinity is negative infinity. The limit of f of x as x approaches infinity is infinity. What did we call this in algebra? The end behavior. What happens to the functional value as x approaches infinity or negative infinity, known as the end behavior. Now, infinite limits, vertical asymptotes VA, reminding you by definition, if the limit of f of x as x approaches a, or a from the left, or a from the right is negative or positive infinity, then VA, short for vertical asymptote, has the equation x equals a. For example, everybody is familiar with the graph of y equals ln x, where the domain is 0 to infinity, and you notice the limit of ln x as x approaches 0 from the right is minus infinity, which makes the y-axis, or x equals 0, its vertical asymptote. Definition: vertical asymptotes, or VA, of the curve y equals f of x is x equals a, as long as one of them holds. It was mentioned here in summary. Another graph you may remember, y equals tan x, and it goes from negative to positive infinity, and it has a bunch of vertical asymptotes. If we go with a complete cycle from negative power 2 to power 2, the limit of tan x as x approaches minus power 2 from the right, that means like, minus 89 degrees roughly. It's negative infinity, and if we go with that, that means x equals minus power 2 is the equation of a vertical asymptote, and so is this one, limit of tan of x as x approaches power 2 from the left, like 89 degrees is infinity, which makes x equals power 2 another vertical asymptote. Again, this is just one complete cycle, and you can go with the tan inverse, and with that being the case, the limit of tan inverse of x as x approaches minus infinity is minus power 2, and the limit of tan inverse of x as x approaches infinity is power 2, and that gives rise to horizontal asymptote y equals power 2 here, y equals negative power 2 here. It's very straightforward, everybody. We want to find limits, and first and foremost, I want to remind you how to find limits. Plug in and observe. If the limit of f of x as x approaches a is a number, you're done. If it's 0 over a number, you're done. It's 0. If it's a number over 0, it's infinity or negative infinity. You have to figure out positive or negative. But in most cases, we end up within the in determinate forms of 0 over 0, infinity over infinity, infinity minus infinity, 1 to the power of infinity, and other forms, which means more work. Right now, if you plug in, you get infinity over infinity. What's the technique? Because this is a rational expression, and the variable x, y, z, t is approaching infinity, the technique is to divide by highest degree term in the denominator. So you're going to divide everything by t squared. And we're going to simplify. Now, because of the limit, every piece goes to 0 except 1. So it becomes 0 over 1 equals 0. And for emphasis, I'm going to write 0 over 1 because I want everybody to know the denominator is anything but 0. The answer becomes 0. Same thing here. You plug in, you get infinity over infinity. Same technique. Because this is a rational expression, t is approaching infinity, you divide by highest degree term in the denominator. This time is t. And you're going to simplify. After you simplify, just plug in. Infinity plus 2, 0, 5, 0. And infinity plus 2 or minus 2 or plus 10,000 or whatever is infinity. If you divide it by any positive value, 5 or 5 billion makes no difference. It is still infinity. The concept of a convergence versus divergence. This one converges, this one diverges. Convergence means you have a limit. Divergence means either negative or positive infinity, or the limit doesn't exist. Same thing here, infinity minus infinity if you plug in. And the technique, whenever you involve a square root, is to multiply by its conjugate. So you're going to multiply by the conjugate and divide by it, reminding you the conjugate of a minus b is a plus b. Their product is a squared minus b squared. So it's going to bring it out. So you're going to multiply and divide by it. And bear in mind, the reason we do that, because this must be 1, and we can do that. And now we just extend the fraction bar, and the denominator remains unchanged. Now the numerator becomes square root of x squared plus 1 quantity squared minus x squared. This is what you get. These two cancel each other. And now if you plug in, you get 1 over infinity plus infinity, and you get 0. What about here? Plug in. E to the power minus t, that means e to the power minus infinity is 0. Why is that? A to the power minus m is 1 over a to the power of m. That means e to the power minus t is 1 over e to the power of t, and 1 over e to the power of infinity is 0. So the answer is 12 over 4 over 3. In other words, you plug in and it works. What about here? If you plug in, you get infinity over negative infinity. Now, this is not a rational expression. It's a fractional format. So we treat it in the same manner, meaning we divide by the highest value in the denominator, which is e to the power of t. And simplify. As you can see, when t goes to infinity, e to the power of t goes to infinity. This goes to 0, this goes to 0. You get positive 1 over negative 3, or negative 1/3. What about here? Plug in infinity minus infinity. By the way, infinity squared, infinity times 10, and infinity divided by 10, all of them are infinity. The technique is factoring. So we're going to factor the x out. And so now infinity times infinity minus 1 is also infinity. Again, we are dealing with a rational expression. And if we plug in, we get infinity over negative infinity. The technique is to divide by highest degree term in the denominator, which is x, and simplify. And I hope you see that the top is infinity plus 1, and the bottom is 0 minus 1. Now this is negative infinity because this is infinity and this is a negative number. It doesn't matter, negative 1 or negative 10 or negative 0.1. Positive over negative is negative, and that's why you want to be careful with a case like this. Find the limit of e to the power minus x plus 2 cosine 3x as x approaches infinity. Let's use the limit laws, cut them into two pieces. I hope you recognize if you work it out, this is 0. But the second piece doesn't have a limit. Why not? Generally speaking, sinusoidal functions, they don't have a limit. The limit of cosine of ax as x goes to infinity does not exist. Same thing for sine. Why? They oscillate between -1 and 1. They keep on oscillating. You want to take the limit here. Again, this is not a rational function, but you treat it as such. If you plug in, you get infinity over infinity. So you divide by highest value. It's not the highest degree because it's not, each one is not a polynomial. So you divide by e to the power of 3x. All right, and I'm going to remind you what happens with the exponential functions. A to the power minus m is 1 over a to the power of m. A to the power of m over a to the power of n is a to the power of n minus m. So I'm going to divide this one by this and this one by this, I get 1. But what happens when I divide these two? I hope you see that I get minus e to the power of minus 6x. Same thing here. I hope everybody can see that this is following. And so each one goes to 0. The answer is 1 over 1 or simply 1 when x approaches infinity. Find the limit of tan inverse of ln x as x approaches 0 from the right. So you can put the 0, actually plug in the following manner. Interchange tan and natural log. So what is the limit of ln x as x approaches 0 from the right? I hope you remember 0 from the right of ln x from the graph, it's negative infinity. I hope you remember that. So this is negative infinity. So think about this, tan inverse of negative infinity. What is it? Let's say it's alpha. What does it mean? Tan of alpha is negative infinity. That's the meaning of it. So what should alpha be? Negative power 2. Okay. I'm reminding you of, this would be the fastest, in my opinion, and easiest way. But reminding you of the graph of a tangent, we just went over that, which one complete cycle has two vertical asymptotes, x equals minus power 2, x equals power 2. Or if you go with the inverse, has two horizontal asymptotes. So the answer is minus power 2. To me, this is the fastest and easiest way. And I'm going to show you here. And theta is negative power 2. All right, either way is fine. I just wanted to remind you of some of the graphs. One of the things that is important, you know the basic graphs, it helps you with a lot of things. So let me erase my one. What about the limit of sine squared over x squared plus 1 as x approaches infinity? Just to give you an idea, you have an idea of when x approaches infinity, the bottom is infinity, but sine is really oscillating between -1 and 1. And it's how do you approach that? We are going to use the squeeze theorem, and we're going to start with sine, reminding everybody that the squeeze theorem says that if G is between F and H, and each one, the left and right, F and H, they go to some limit. When you take the limit as x approaches A, the middle one works in the same manner. So we are going to work this out in the same manner, starting with sine. Sine is between -1 and 1. Sine squared, if I square it, is between 0 and 1. Again, I want to remind you why. It's not that you're going to square that because it's a negative number. That's not any negative number, -5, negative, you have to really go with 0. I want you to know that. Of course, if it's -5, squaring it is 25, so it can go all the way to 20. In any event, so sine squared is between 0 and 1. We are going to make it look like this. So x squared plus 1 in the denominator is missing. So we're going to multiply by 1 over x squared plus 1. And remember, with inequality, it can flip over if you multiply or divide by negative. This is always positive. Left side doesn't change. The right side becomes 1 over x squared plus 1. And this is exactly what you want. Now, the left side, you take a limit as x approaches infinity is 0. So is the right side. The limit of 1 over x squared plus 1 as x approaches infinity is 0. So the middle one, the limit of sine squared over x squared plus 1 as x approaches infinity must be 0 by the squeeze theorem. Okay. By the squeeze theorem. It's very straightforward, everybody. Find asymptotes. Well, you're going to take the limit of the function as x approaches plus minus infinity for the horizontal asymptotes. And to do so, you are going to divide the top and the bottom by highest degree term in the denominator, which is x squared. You get this one. This goes to 0. Everything goes to 0 except the two numbers, so 2/3. When x approaches infinity or negative infinity, this goes to 0, this goes to 0, this goes to 0, okay? And so the horizontal asymptote has the equation y equals 2/3. Vertical asymptote, just you can go with the definition or just set the denominator equal to 0. And this is simple factoring because 3 is a prime number, it's 1 and 3, and -1 is 1 and -1, one of them. So you have to make sure the middle term works, just so you know. This is 3x squared, this is -1. To make sure the middle term works, check it out. The middle term, this one is minus x. This one is 3x. Do they add up to the middle term? So yes, x is either 1/3 or -1. So there are two vertical asymptotes. Find a formula for a function. Let me erase my work. That has vertical asymptote x equals 1, x equals 3, horizontal asymptote y equals 1. So let's start by setting up a function, a fraction bar, and starting with this one, x minus 1 in the denominator. This one, we need x minus 3 in the denominator. And now, if the horizontal asymptote is y equals 1, notice the denominator, if I multiply these two, I get x squared minus 4x plus 3. This is the only one that matters. At top, I have to have x squared with the coefficient 1 because the horizontal asymptote is 1. Let's say this was 5. I would put 5 x squared here. Again, this is one of the possibilities. It doesn't mean this is the only answer. This is one possibility. For example, if I said x squared plus 5, that works too. Minus 1, that works. So there are infinitely many answers. This is one possibility, everybody.